Next, I'll be talking about oxo-biodegradable plastics. This technology is based on a very small amount of pro-degradant additive being introduced into the manufacturing process, thereby changing the behavior of the plastic. Degradation begins when the programmed service life is over, as controlled by the additive formulation, and the product is no longer required. During biodegradation, the plastic does not just fragment, but will be consumed by bacteria and fungi after the additive has reduced the molecular. First, harvested corn crop is soaked and ground so that the endosperm can be retrieved from gluten and fiber. Next, producers add enzymes to the endosperm, which converts into dextrose, a type of glucose. Then, the addition of bacterial cultures causes dextrose to ferment into lactic acid. The resulting acid consists of lactide molecules which bond into long chains, forming polylactic acid plastic, which can be then spun off into fibers or melted to take any form, and it can be biodegraded. In a compost heap, fungi and bacteria found in soil breaks down PLA into its basic parts. Under the proper aerobic conditions, with heat and moisture, PLA will compose like any other organic material. The microorganisms found in compost consumes the corn plastic and break it down into humus, which is a nutrient-packed soil-like substance that acts as natural plant food. The waste products are carbon dioxide and water. The materials only have to spend a month or two in a high humidity composting environment at around 60 degrees Celsius before they return to the earth from which they were originally grown. Structure to a level which permits living microorganisms access to the carbon and hydrogen. This process continues until the material has biodegraded to nothing more than carbon dioxide, water, and humus. The length of time it takes for oxo-biodegradable products to degrade can be programmed at the time of manufacturing, and can be as little as a few months or as much as a few years. They're protected from degradation by special antioxidants until ready for use, and storage life will be extended if the products are kept in cool and dark conditions.
Researchers, smart as me of course, have found that a wide variety of bacteria synthesize a special kind of PHA polymer called poly-B-hydroxybutyrate, or PHB. Ever thought bacteria had no fat? Well, PHB serves as an energy storage material for bacteria. Bacteria relies on carbon for energy, and PHB is produced when there is excess carbon in the bacteria. PHB is used when bacteria are in nutrient-poor environments, but a lot of PHB will be formed when bacteria are in proper conditions. The best thing about PHAs are that because they are of biological origin, they degrade relatively quickly and completely. Bacteria will break down the PHA into CO2 and H2O. However, PHA-based plastic will not decompose in a microbially inactive environment such as a sanitary landfill with no active microorganisms. Another benefit of PHA-based plastics is the ability to control the chemical and physical properties of the polymer. We can tailor-make polymers at a molecular level. If glucose is used as a substrate for producing bacteria, PHB will be formed. Evaluate. A 5-carbon fatty acid is used as a substrate, poly-B-valuate or PHV will be formed. So, if you want to mix PHB and PHV to form a special type of plastic, we add both glucose and valuic acid. A 20% PHV and 80% PHB combination will be formed. This combination is stronger and more flexible than regular PHB.